Okay, good morning. So welcome to our third online lecture, and starting from the beginning of the semester, that will be lecture 16. And today we will talk about two topics. So the first topic will be the homomorphisms of free groups. Homomorphisms of free groups. And in the homomorphism of the free groups, the most important theorem for us will be the so-called universal property of free groups. And after that, we will move on to the group presentations. Now, this time I'm lecturing from my home, so I apologize for all external noises, etc., which might appear. Okay, so let's start with the first part, and let's start by formulating the most important theorem about the homomorphisms of free groups. So that will be theorem 1. And this is the so-called universal property of free groups. Universal property of free groups. So it is formulated as follows. So let G be a free group. With alphabet A. Be a free group with alphabet A. Also, we say that this is a free group generated by the set A. So it consists of elements AI, which are called letters. I runs over the indexing set. And let G prime be any group. And let G prime be any group. Then the statement of the theorem is that for every map, F, from A to G prime. Again, A is not a group, so this is just some map which sends elements A to the G prime. There exists a unique group homomorphism. Group homomorphism phi from the free group generated by A to G prime, such that phi, when restricted to A, so A can be thought as a subset of f of A, equals to f. So this can be summarized on the following diagram. So suppose we have A, right? And that's the subset of our group G, which is a free group generated by A. And what can we say is that if we have any possible map F to a group G prime, then this map uniquely extends to a group homomorphism. Phi, so there exists a unique group homomorphism phi, which when restricted to the subset A coincides with F. Now, any questions about the formulation of the universal property before we move on to the proof? So if you want to ask questions, please unmute and ask questions. Okay, so then let's move on to the proof.
Sorry, can you go back to the previous slide for a quick second?
Sure, here we go.
Thank you.
Okay. Now I'll just repeat after the lecture. Of course, I will upload all the slides to bCourses. So okay, so let's start the proof. Now for the proof, we will just present an explicit formula for this group homomorphism phi. So let's define phi. So that should be a map from f of a to g prime as follows. So for every word w, which can be written as ai1 to the power m1, ai2 to the power m2, all the way to the aik to the power mk. So that's in f of a. We assign, well, we define phi of w to be the following guy. So we take f of a sub a1. So that's an element of g prime, right? That's an element of g prime. It's an element of g prime. And we raise it to the power m1. Then we take f of a sub i2 and raise it to the power m2, and so on, all the way to f of iak, which is then raised to the power mk. Now the thing to note here is that powers and multiplication are in J prime. Powers and multiplication are in J prime. So we just, because it's a group, we can take powers of element, we can multiply them. So this is the way we define the function from the free group with alphabet A to J prime. And now we will prove 3 claims about it. Well, actually, so the first 2 claims deal with existence of the homomorphism. Basically, the first 2 claims will deal with the fact that this map is well defined on a free group, and it is a homomorphism. So claim 0. Now note that above we introduced phi of w for every word. So the first thing one need to prove is that the above defined, well, the above phi is well defined on equivalence classes. Equivalence classes of words in f of a, because the elements of f of a are not just words, they are equivalent classes of word. Single element of a free group can be represented by infinitely many words. And what this claim 0 is saying is that no matter which particular representative of this equivalence class you take, then this formula actually gives you one and the same element of G prime. Okay, I'm not going to go over all the details needed to prove claim 0, but basically you have to prove that this map behaves well under elementary contractions and expansions. So that's now claim 1. So once we assumed claim 0, we now can indeed talk about the function from the free group with alphabet A to G prime. So the claim 1 would be is that the above defined phi satisfies the homomorphism property. Above defined phi satisfies phi's homomorphism property. Okay, so indeed, let's look at phi applied to the product of two words, right? So what it will be? It will be the following product of elements. F, so suppose the first word was A1. Suppose the first was AI1 to the M1, all the way to the AIK to the MK. And the second word was BJ1 to the power N1, all the way to BJL to the power NL. So the result will be A1 to the power M1, all the way to F of AIK to the power MK, and finally F of B J1 to the power N1, all the way to F of BJL to the power NL. Now if we group the terms here like this, then we will get precisely that this is the same as phi of W1 multiplied by phi of W2. Now note that for the proof of claim 1, it is essential that we assume claim 0. In other words, that instead of considering that we can take any possible representatives W1 and W2 of the equivalence class of words, and we can say that the result of the multiplication is just concatenation of the two. Okay, so the first thing, kind of claim 0 and claim 1 all together implies existence. Existence. So before I move on to the next slide, any questions about claim 0 or claim 1 in the proof? Okay, so now let's move on to the uniqueness. Claim 2. Uniqueness. And here we would say that if psi from the free group generated by A to G prime is another group homomorphism, satisfying the following condition, that psi restricted to A is the same as our original map F, then necessarily psi must be equal to phi. Well, psi must be equal to phi. Well, and here, indeed, first of all, we know that psi of all letters, AI1 equals to phi of AI1 and must be equal to f of AI1, right? For all I1 in the indexing set, a capital. Well, then because psi is a homomorphism, what we know for sure is that if we raise the element AI1 to the power m1, that must be the same as psi of AI1 raised to the power m1, and that must be f of AI1 raised to the power m1, right? And similarly, if we take the product of AI1 to the AM1 all the way to the AIK to the power MK, then the result must be the product of AI1 to the power M1 all the way AIK to the power MK, and that must be exactly the formula we used to define phi on the first place. So this is f of AI1 raised to the power M1 all the way to f of IK raised to the power MK. And that's exactly what was phi of this word. IK equals to MK. Now, the thing to note here is that multiplication and powers on the right-hand side, so multiplication, and powers are in G prime. Okay. So as functions, phi and psi must coincide, and that implies the uniqueness of the homomorphism. So this concludes the proof of the theorem 1. So any questions so far? Now, corollary, corollary 1, in order to define homomorphism phi from the free group on A to G prime, it is enough to specify where the generators go. Phi where generators go. There's go, and there is, well, and there is no restrictions. On where they can go. And this explains why this group are called free. This is why these groups are called free. Okay. Now, this universal property of free groups has many important applications. And one of the immediate applications would be the theorem about the rank of the free group. So that will be our theorem 2. And let now A and B be different alphabets, different alphabets, then the free group on A is isomorphic to the free group on B if and only if and only if A and B has the same cardinality. Now, so remark on proof. Remark on proof. I wouldn't go over the entire proof, and instead I will explain what is easy and what is hard in the proof. Now, first of all, the opposite implication, the reverse implication, is immediate. Namely, if you have two sets with the same cardinality, right? This means that there is a bijection between the sets A and B, and this bijection actually gives rise to an isomorphism between F and A, between the free group on A and the free group on B. So this part is easy. Now, however, the opposite implication is actually not that easy. And let me explain why this part is not immediate. And it is not immediate precisely because there are complicated isomorphisms between free groups. There are many interesting isomorphisms between free groups which are not coming from identification of letters. And let me talk about the two examples. One will be an example of an isomorphism, and the other will be example of just a homomorphism, which is actually not surjective. So, example 1. So let's look at the alphabet, which consists of two letters, X and Y. And another alphabet, which consists of three letters, Z and W. And let's look at the phi from A to B, which sends X to Z inverse W squared, and Y to W inverse Z. My theorem 1 there exists. Oh, sorry. I made a typo. And let me see, where's the eraser? Of course, this will be a map not from A to B, but this will be a map from f of A to f of B. There exists a unique such homomorphism. And claim phi is an isomorphism. So the proof will be left as homework. So the story about the isomorphisms of free groups is actually not that easy, that you just identify letters of the alphabet between the free groups. There exists much more complicated homomorphisms. Oh, well, there exists much more complicated isomorphisms, and in this regard, let me talk about a non-example. So again, A will be the same alphabet with 2 letters, and B will be the same alphabet with 2 letters. And phi will be a homomorphism from f of A to f of B, which sends x to the same z inverse w squared, and y is being sent to z. Then claim is that phi is not surjective. And again, proof left as homework. Okay. However, the previous theorem is true. Let me scroll back for a second, and that if you do know that the 2 free groups are isomorphic, then you must have that the corresponding alphabets have the same cardinality. And this allows us to introduce the following definition of the rank of the free group. Definition 1. Now, if G is a free group generated by A, so we call the cardinality of A, the rank of a free group. Well, note that theorem 2 implies that isomorphic free groups must have the same rank. Okay, so in fact, this rank, it kind of classifies completely all possible free groups. So the two free groups, they are isomorphic if and only if they have the same rank, and they are not isomorphic if they have different rank. So any questions so far? Now, finally, to conclude our discussion about free groups, let me make the following remark, which goes slightly beyond the scope of the course, slightly beyond the scope of the course. So those of you who will be taking graduate abstract algebra will learn this in much more details, but it's still worth mentioning that universal property of free groups, property of free groups, is actually defining. And by defining, I mean that it defines a free group uniquely up to isomorphism. So namely, proposition 1 would be as follows. Now, if G is a group, and A in G is a subset, for which the statement of theorem 1 is true, of theorem 1 is true, then G must be isomorphic to, so not necessarily equals to, but isomorphic to a free group generated by A. So that's a remarkable property of free groups, which in kind of graduate abstract algebra, in fact, used as a definition of a free group. So the free group can be defined up to isomorphism, of course, as a group satisfying the universal property for a certain subset. Okay, so any questions about the free groups and homomorphisms of free groups? Okay, so please don't hesitate to ask questions. I know it's kind of a little bit strange when the discussion is over in Zoom, but please feel free to ask all possible questions. Okay, so then let's move on to the second part of our lecture, which will and let's talk about the group presentations. Group presentations. Okay, and so why presentations? So what's behind this name? So it is possible to define a group, in fact, in terms of generators and relations. So in some cases, it is convenient to define a group in terms of generators and relations. And relations. So note that theorem 1 implies the following corollary. Corollary 2. Every group G is isomorphic to an image of the group homomorphism from f of A to G. For some A, and some phi. So in other words, we can describe every group, as a quotient of a free group. And that's precisely what we will talk about in the second part of our lecture.
Quick question.
Yes?
So when we say that the phi of f of A goes to G, that means that by the previous theorem that the size of the rank of A needs to be equal to the rank of G?
That's a good question. Let me stress this one. This once again, that most important, this is every group, not necessarily free. Not necessarily free. So that's a good point. Thank you. So before we talked about in the theorem 2, we talked about isomorphisms between free groups.
Mm-hmm.
And right now we don't assume that G is free anymore. So of course,
Okay.
free groups is a very particular example of a group. Very simple and particular example of a group. Of course, there are much more groups than the free groups. And in particular, all the groups we have studied so far, except for the Z, are not actually free. But we will come to that in a few minutes.
Okay, thank you.
So, any more questions so far? Thank you very much for asking, because that's important to clarify all these moments before we proceed. Here we go. Okay, so now let A be an alphabet and let R be any subset of a free group. Be any subset of a free group on A. So R is just some subset, consists of different words. So with R, we can associate with R we can associate a subgroup of f of a defined as the smallest normal subgroup of f of a containing R. So note that we can talk about the smallest normal subgroup. Note that we can talk about the smallest normal subgroup because the intersection of two normal subgroups is again a normal subgroup. Intersection of two normal subgroups one intersect with two is again normal, and that's proof was in the homework. Proof was one of the homework. So you can basically look at all possible subgroups, right, in the free group, which would contain this subset R, and take their intersection. And because the intersection is will be a normal subgroup, then there would exist the smallest normal subgroup in the free group containing R. So now the definition. Definition 2. Is that the group generated by A with relations R is nothing as the quotient group of a free group by this normal subgroup N. Okay, so this is one of the definitions where you can prove that this is a group. You can define this group, right? However, this definition doesn't tell you anything about G as a set at all. And so this is highly inconstructive in a sense and rather abstract. So to get some idea of that, let's look at the examples. And
really quickly,
yes?
The A that we're talking about here is the alphabet, correct?
Yes.
Okay.
The A is the alphabet, and R is a subset of a free group called relations. Okay, so let's start with example, and that will be example 3. Suppose A is a singleton set and R is an empty set. Empty set, that's of course the subset of f of A. Okay, so what do we know about the f of A? What do we know about the f of A as a set? What are possible words we can get? That's the question to the audience.
X.
Good, we can get X. What else we can get? So remember, the words are just kind of formal powers of X, right? So there is X, which is X to the 1. There is X squared. There is X cubed. And of course, there is an X to the 0, which is an identity, right? And also there is X to the minus 1, etc. Okay, so can you suggest what this group can be isomorphic to?
Is it just the z's, all integers, all the groups generated
Exactly.
by one number?
Great. So and this free group with a single generator is isomorphic to integers. So that's the familiar group. So free group of rank 1 is isomorphic to Z. And because R is empty, because we have that R is empty, this implies that the smallest normal subgroup containing R is the trivial group. And this means that f of A quotient by n isomorphic to f of A, which is Z. So we can think of Z as a group generated by a single element with no relations. We can think of Z as a group generated by a single element with no relations. Okay, so now let's look at the smallest possible, now let's look at the simplest possible example of a group with relations. So let's look at example 4. Let's look at example 4. And let's say that the group, so first of all, let me move back. Sorry about that. I forgot to introduce the notations. Now here, in this case, we write G as generated by A subject to relations R. Now note that this is slightly different from what we used angle brackets before. We already used angle brackets to say that we have a group generated by certain elements, but before we had this binary operation to be given from the start. So we had some large set with a binary operation, and then we say that the group generated by a collection of elements is precisely the smallest subgroup containing these elements. Now this is slightly different because here this defines a group not in terms of a subgroup of a different group, but it actually defines the binary operation at the same time. So the right-hand side defines the group here. Okay. So we would write in these notations, we would write that Z is isomorphic to a group X with no relations. Oh, with a group generated by X with no relation. So let's move on to example 4. Example 4. And let's look at the group G. Again, generated by single element, subject to relations x to the n. Okay, so again, what do we have? We have f of a. We have f of a to be kind of the set of all powers of x. J belongs to integers. And that's isomorphic to group Z. Now, what about the subgroup N? So what is the smallest normal subgroup containing L? Smallest normal subgroup containing x to the n. So what this will be?
Is it the group generated by x to the n?
Great, yeah. So in this case, because kind of f of a, the rank 1 free group is abelian, right? So every subgroup is normal. So the only thing we need to consider is a subgroup generated by xn. So this is the set of all powers x to the n k, where k belongs to integers. Okay, so this is, sometimes it's denoted as n. And z. Okay, so what we will get as f of a quotient by n.
Would you divide it into all the numbers into different equivalence classes? So you'd have n different
Great.
kind of sets.
That's right.
All the x0 and then x1, x2.
Perfect. So the first element of the set will be the equivalence class of the x0. The second element will be the equivalence class of the x to the 1. Or better say the coset, right? Containing x squared all the way to x to the n minus 1. And we've seen this group already, right? So it is isomorphic to
Zn.
Yeah, it is isomorphic to Zn. Great, thank you. Okay, so what we just shown is that this guy is isomorphic to Zn. So that's the way how to define the Zn using generators and relations. So there's one generator and one relation. Okay. Now let's move to the slightly more complicated example. Well, let's move on to the slightly more complicated way of defining a familiar group. And let's look at the group G, which is generated by elements x and y, subject to the following relation: xy, x inverse, y inverse. Okay, so the free group now is actually quite complicated. So f of a So what it will contain? Well, it will contain, of course, all possible words in XY, all possible words in XY, right? So what we'll find there, well, of course, we'll find an empty word, which is an identity. We will find X, we will find Y, we will find XY, we will find YX, we will find X inverse, Y, etc. And they are all different. So they are not equal to each other. So there are tons of elements. Now what will be N? So that's smallest normal subgroup, smallest normal subgroup containing the commutator of XY, just XY, X inverse, Y inverse. And this is actually will be C, the commutator subgroup. Subgroup of f of A. We know that the commutator subgroup is normal, right? We know that it will contain all commutators. Now, the slightly more difficult thing to say here is that why we need this subgroup to contain all other commutators as well, not just commutator of xy. But I will kind of hide this under the rug for now. Okay, so what do we get as f of A? F of A quotient by n. So what are the cosets of the commutator subgroup? Kind of know that this is a billion, right? And if it is a billion, then we can move all kind of x's and y pass through each other. So really, as a set, this quotient will be xm, ym. Oh, sorry. Y to the n, where mn are integers. And it is actually isomorphic to z cross z. Now, in this example, I skipped a couple of parts under the rug, and that's actually a manifestation of a general fact. When you have the definition of group in terms of generators and relations, in general, it is very hard to find this group explicitly, meaning to describe G as a set and describe the multiplication rules. Now, in the simplest examples, like in example 3 and 4, we can actually prove all the steps, right? And conclude what the group we're getting. And when this is possible, we say that the word problem is solvable.
Really quickly,
yes?
Could you go over one more time how you formed that f of A quotient n group?
I'll just give a sketch because the kind of the full proof, as you might see it, as you might guess, will take a while in this example.
Oh, okay.
So sketch, because f of A mod n is commutative, you can say that kind of x, if you have w1, x1 to the, y to the k, x to the l, w2, this is the same as w1, xl, YKW2, right? So we can move all powers of x to the left and present all element uniquely in this form, as all element of the quotient group can be presented uniquely in this form as x to the m, y to the n. But again, there are some technicalities. So does it clarify roughly how one would prove that?
I'm a little confused how we're using the commutator subgroup in this application. Like when we're trying to find the quotient group, we know that n is the commutator group subgroup. So then how are we applying that to divide?
That's an excellent question. And remember a couple lectures ago when we talked about the commutator subgroup, we said that the commutator subgroup is important precisely because it gives us the criterion when the quotient group is abelian. So if we have a normal subgroup, let's say H, right? Then the quotient G mod H is abelian if and only if the commutator subgroup is contained in H.
Mm-hmm.
So in particular, the quotient by the commutator subgroup gives us a abelian group.
Okay.
So that's...
So it's because it was the commutator subgroup that we were able to say that FA over N is commutative.
That's right, exactly.
Okay, thank you.
Thank you. Okay. So okay, so let's introduce some standard terminology here. So let G be a group defined in terms of generators and relations. So it is generated by A, subject to relations R. So when A is finite, we say that G is finitely generated. Finitely generated. Well, when both A and R are finite, we say that G is finitely presented. Finitely presented. Now, when we can construct an algorithm which determines if W equals A1 to the AI1 to the M1, I2 to the M2, AI2, Ik to the Mk equals E for all W and G. We say that we can solve the word problem. Word problem in G. And let me put here in red. In general, presentations of groups are very complicated. In particular, there are groups for which the word problem cannot be solved. Okay, now, and just to give you an example here, let's, well, this will be example of the group where the word problem actually can be solved. Let's say that. Example, and that's example 6 or something. G. So suppose you have a group with 3 generators subject to the following relations. So you have x, y, x inverse y to the negative 2, y, z, y inverse z to the negative 2, and zx, z inverse x to the negative 2. And it is actually a presentation of a trivial group. Is actually a presentation of a trivial group. And one needs some calculations to see that. This is just an illustration how the group presentations can be very hard. So
for these examples, where we're trying to say its presentation is the trivia group, when we do this, we always say that G is equal to a quotient group. So if it's a trivia group, are we saying that it's
isomorphic?
Only cosets are the group itself and the identity?
Exactly.
Okay.
Well, no, the only cosets are the only cosets of n will be the entire G. So basically, n equals G.
Oh, okay.
So this means n equals G, and oh, sorry, not G. N equals f of a.
F of a, okay.
N equals f of a, and G equals trivial group.
Okay.
Quotient is trivial. Yes. So so this is true for this example. However, in order to see that, you need some lengthy computation. You need to show that this n must contain everything, and that's not a very easy job. So in general, these groups defined in terms of generators and relations, they are much easier to define rather than to work with them. So that's the whole kind of the moral of the story. So in particular, there is a very important, examples of groups in topology which can be easily described. They will give you kind of ultimate not invariant, but it's absolutely impossible to say whether the two groups having different presentations are isomorphic to each other, and that's kind of the subtle point here. Okay, so in the conclusion of the lecture, let's look actually at the example, which is both non-trivial and at the same time the word problem is solvable. Okay. Still, there are many important groups for which there exist non-trivial presentations and word problem can be solved. And actually, we already talked about this, and let me probably separate it as part 3 of this lecture. So here we will talk about 2 presentations of dihedral group. Group. Okay, so let G1 be defined as a group generated by two elements, subject to the following relations. That S squared R to the N and SR SR are all equal to identity. So this means that S squared equals to R to the N equals to SR equals E in G1. Okay, so we claim that G1 is nothing as a dihedral group up to isomorphism. And kind of sketch, again, the proof will probably appear in the homework, maybe as an optional problem. Kind of here's the sketch of the proof. First of all, prove that step 1, prove that every word prove that every word can be presented as one of the following. So it must be either an empty word, or it can be some power of R squared all the way to the Rn minus 1, or it can be S, Rs, R squared S, all the way to the Rn minus 1 S. So using these relations, which are in blue now, you can show that you can bring all words in the following form. Step 2, and that's actually the hard one. Prove that none of the words above are equal to each other. G1. And altogether, this will give you an isomorphic to the an isomorphism to the Gn. G1 isomorphic to the G2 sub to n. Okay. So, any questions so far? So this is an example of a finitely presented group where the word problem can be solved. Now there is another presentation of the dihedral group. Another presentation of G sub to n. So let's look at the group G2, subject to the following, again, generated by two elements, S1, S2, subject to the following relations, that S1 squared, S2 squared, and S1, S2 to the power n are equal to an identity. S1 squared equals S2 squared equals S1, S2, n equal to e. That claim is G2 also isomorphic to G sub to the n. And kind of sketch of the proof First of all, you prove that G2 as a set is the following thing: is the products S1, S2, S1, S2, S1 all the way, k times, where k is from 0 all the way to 2n minus 1. And then you prove that all elements are distinct, and that every element using this relation can be brought to that form. Kind of moral. The same group can have very different presentations. And different presentations in terms of generators and relations of generators and relations. Okay, so also I have to mention here that recall homework about Cayley diagrams. Cayley diagrams. So then there this presentation of the dihedral group actually appeared. Remember there was a problem where you need to show that there exists a group generated of order 2n, which is generated by two elements of order 2. Okay, so on this kind of on this point, I would like to conclude the part of the course which deals with the group theory. And starting from next time, we will introduce the notion of a ring. And we will start our last third of the course, which will deal with the theory of rings. So hopefully this this story about generators and relations illustrates that there is much more to study in the group theory. To those of you who will continue study of abstract algebra in Math-113 or graduate algebra course. But that's it for today, so I'll be glad to answer your questions, and then I will restart with office hours.
Will there be any changes with midterm 2?
Oh, that's a good point. So let me make this announcement now. For sure, the midterm 2 will be online. Now, I haven't yet decided about the exact format, but I will post the announcement this week, and this will kind of explain whether it will count towards grade, etc. But definitely up until the week of final exams, there will be no requirement to attend anything in person. So the midterm 2 will be online, and I'm still deciding on the exact format. Yeah, thank you. That's.
It will be the Tuesday we get back from spring break, correct?
Yes.
Okay, thank you.
Thank you. Yes. Okay.